Here are two balls, starting at exactly the same height. One is simply dropped. The other is launched sideways at high speed. So, which one reaches the ground first? Take a guess before I show you. Ready? Watch. They hit the ground at exactly the same moment. Surprising, isn't it? Let's slow it down. Pause at any instant, and you'll notice something remarkable. The two balls are always at the same height. Always. The sideways motion doesn't slow the fall, and the fall doesn't slow the sideways motion. The two motions are completely independent. But why? The answer is gravity. Watch the force itself, not the ball. Gravity pulls with the same strength, in the same direction, every moment, straight down. It never leans forward, and it never weakens as the ball speeds up. More importantly, there's no sideways pull at all. None. Gravity changes only the vertical motion because that's the only direction it acts. That's why the horizontal and vertical motions stay completely independent. Let's look at the sideways motion first. Nothing pushes it forward, and nothing slows it down. So its horizontal speed stays constant. 20 meters in the first second. Another 20 in the next. Another 20 after that. Equal distances in equal times. Simple, and that's exactly what makes it easy to understand. Now for the downward motion. Here, gravity is constantly pulling. Every second, it increases the downward speed by about 10 meters per second. So the distances covered each second keep growing, about 5 meters in the first second, 15 in the next, then 25 in the third. Now notice something important. We didn't invent two different rules. They're both the same equation we learned in part 2. For the sideways motion, the acceleration is 0, so the acceleration term disappears. You're left with distance equals speed times time. For the vertical motion, the ball starts from rest, so the initial speed is 0. This time, the first term disappears. Same equation. Different quantities become 0. There's nothing new to memorize, you already know this equation. Now let both motions happen together. Constant steps across. Bigger and bigger steps downward. Across, down. Across, further down. Across, further still. And without anyone drawing it on purpose, a beautiful curve appears. That's a parabola, the natural path created when constant horizontal motion combines with accelerated vertical motion. Let's apply it. A probe leaves a rocket horizontally at 20 meters per second from a height of 45 meters. Where does it land? Don't start with the horizontal motion. First, ask the vertical question. How long does it take to fall 45 meters? 3 seconds. Once you know the time, the horizontal part is easy. 20 meters per second for 3 seconds gives 60 meters. The vertical motion tells you how long. The horizontal motion tells you how far. Now, how fast is it moving downward when it hits the ground? We can solve it in two different ways. The first uses time. 3 seconds of acceleration at 10 meters per second squared gives 30 meters per second downward. The second doesn't use time at all. It uses the distance fallen, 45 meters. Plug that into the third equation, and after taking the square root, you get the same answer, 30 meters per second downward. Different information. Same result. That's why these aren't just formulas to memorize, they're tools. Use the one that matches the information you're given. But that's only the vertical speed. At the moment of impact, the probe is still moving sideways at 20 meters per second while also moving downward at 30. Since those velocities are at right angles, you can't simply add them. They combine as vectors. Using Pythagoras, the resultant speed is the square root of 20 squared plus 30 squared, about 36 meters per second, directed downward and forward. It's exactly the same vector triangle we used when walking to the ice cream shop. Let's wrap it up. One path, but two completely independent motions. Sideways, there's no acceleration, so the speed stays constant. Downward, gravity accelerates the motion from rest, so the distance covered each second keeps increasing. Because gravity acts only downward, you solve the horizontal and vertical motions separately using the equations you already know, then combine the results as vectors. Now it's your turn. The probe still drops from 45 meters, but this time it's launched sideways at 40 meters per second instead of 20. Does it stay in the air any longer? And where does it land? Leave your answers in the comments. And here's one final question that catches almost everyone. Could you avoid a falling ball simply by running faster?